Hello everyone, I'm going to present mixed reality and real-time X-ray simulation in vet radiography training. This project is supported by the Irish Research Council. I'm Xuanhui from University College Dublin, collaborating with Antonella from the School of Veterinary Medicine on this project. In diagnostic imaging training, it is important that students understand how to use X-ray equipment safely. However, creating a practical training session is challenged by class size, availability of staff and horses, radiation safety, and ethical concerns. Previously, to overcome the challenges, we proposed a mixed reality system that lets students develop skills in radiographic positioning. This system allowed students to get hands-on practice and collaboration using preset X-ray images. For this study, since the only object that needs virtual visualization is the animal, we incorporated real equipment into a mixed reality system. Our aim was to explore whether integrating real equipment enhances realism and improves DI training compared with a fully virtual setup. Furthermore, real-time X-ray images can be synthesized to enhance training effectiveness. Real-time radiography simulation provides safe, instant feedback during training. Research has shown that combining physical and digital elements in a mixed reality environment creates an immersive and effective training experience. In this study, we proposed a tracker-based MRDI teaching system with real-time X-ray synthesis. The system employs a real-time X-ray machine and an image detector holder tracked by two HTC Vive base stations connected to a host laptop via 3 Vive trackers. Additionally, 3 MetaQuest 3 headsets were used to create a collaborative MR environment. Here is the diagram of the system's architecture. Trackers are attached to real equipment, and through wireless syncing, the transforms are sent to the host machine. They are then shared with the user over the network. At this stage, user can manipulate both physical equipment and virtual annotations. When user triggers the exposure button, all data is sent to the host machine and to start the simulation process. We used a CT scan of a horse limb to generate a 3D model using Slicer 3D. The model was then rigged to match the standing pose of the virtual horse in Blender. This model replaced the original horse limb in Unity. Once the exposure button is triggered, the GVXR library generates the simulated X-ray image, and the result is displayed on the monitor like the real DI procedure. The Depth API let virtual content to be occluded by real-world objects, further enhancing the sense of local presence. The experiment was conducted in the radiation room. We prepared an interaction tutorial to ensure that participants understood how to interact with the virtual elements. In VEMR system, user can move the virtual machine. Collaborating the radiation beam, and measure the distance using the virtual ruler. The radiation beam can be visualized to teach safety rules. And the markers can be positioned just like in the real procedure. And when the exposure button is pressed, the image will show on the host machine. Here's an example of experts trying out the VEMR system. In PEMR system, user needs to move real image detector holder and the real X-ray machine. They can adjust the same settings through the virtual annotations. Here's an example of students trying out the PEMR system. We conducted a user-centered comparative cross-sectional study to evaluate PEMR and compare it to VEMR. We measured students' scores and the time taken to complete a DI procedure and tracked their behavior through movement data. Participants switched between two systems to balance exposure, mitigating knowledge carryover and fatigue. PEMR refers to the system we proposed, while VEMR is the previous system combined with the real-time X-ray synthesis. 20 vet students and 4 DI experts participated in the study. Most reported limited VR gaming experience. After filling the pre-questionnaires, participants went through a hand tracking tutorial. Then, working in pairs, they performed 2 X-ray procedures, switching roles between scans. A lecturer wearing a HMD guided the students, while experts complete the task independently. After the first session, participants fill out a questionnaire before repeating the procedure with the alternative system. Lastly, they complete a final questionnaire. Under real-time guidance, the students' performance improved significantly during PEMR session, eventually aligning with experts' performance. This result indicates that the system can be an effective teaching tool. In contrast, students performed constantly in VEMR and significantly better than in PEMR. Handling physical equipment is challenging, while virtual equipment is easier to use as it flows in the mid-air. There was no significant improvement in the time students spent taking X-ray after the practical session in either system, highlighting a notable performance gap between experts and students even with on-site guidance. No significant difference was observed in the time required to take first X-ray image between the system, while a significant difference appeared for the last image. As shown in the heat map, users spend most of their time around the X-ray machine and the image detector, moving more when using the virtual equipment. Although equipment's move pattern were similar in both systems, real equipment requires more frequent and small adjustments. Holding the real detector holder also demanded more efforts, resulting in less precise positioning compared to the virtual setup. While virtual equipment closely mimic the real case, it cannot fully replace the hands-on training. In comparison to the benchmark, both systems reached the top 10% of the results on the user experience questionnaire. According to the NASA TLX questionnaire, all items are rated at relatively low levels. Most participants preferred VMR because it was easy to use and understand. However, many also agreed that incorporating real equipment made the system more realistic and was necessary. They expressed equal positive opinions regarding the potential adoptions of the system in the actual training, noting that both systems have their own advantages. Physical equipment enhances realism by direct control, while virtual system simplifies trainings and allows for solo practice. The optimal approach, therefore, is the one that combines both methods. In a pilot test, students couldn't perform X-ray independently, so no baseline data were gathered in the actual experiment. The network was not stable, that leads to resets and occasional misalignment of virtual annotations. Moving forward, we plan to conduct a longitudinal study with the vet students to assess the training impact and explore its potential for OSCE-like evaluations. Thank you.